Every AI lab says the same thing. Our new model is the smartest one yet. And here's the uncomfortable question almost nobody asks back. How would you actually know? Because it turns out measuring intelligence is far harder than building it. We've followed Claude from how it's built, through scaling, and into reasoning. Models that think longer to answer better. But all of that rests on one thing we've quietly taken for granted: the ability to tell whether a model is any good at all. Today, evaluation. How we test these systems, why the tests keep breaking, and why measuring progress may be the hardest problem in the whole field. We'll cover what a benchmark is, why they stop working, the cheating that happens by accident, how testing is evolving, and why evaluation is the real bottleneck now. Start with the basic tool, the benchmark. It's simple. You take a big fixed set of questions with known correct answers, thousands of them, spread across math, science, coding, reading comprehension. You let the model answer everyone, and you score it. 90% right, 70% right, a single clean number at the end. Do this with the exact same test for every model, and suddenly you can compare them on even footing. That number is what fills the charts you see at every launch, what fuels the leaderboards, what lets a lab stand up and say this version beats the last one. And for a long time, benchmarks were genuinely, enormously useful. They gave the whole field a shared yardstick, a way to turn a vague feeling that a model seems smarter into something concrete you could point at, track over time, and argue about with numbers instead of vibes. The trouble is, what happens when everyone in the world starts aiming at the exact same yardstick, and when that yardstick was only ever a rough stand-in for the thing you actually care about? Here's the first problem. Benchmarks wear out. When a good model scores 50% on a hard test, that test is doing its job beautifully. It separates the strong from the weak, and there's plenty of room left to climb. But models improve fast, and soon they're scoring 95, 98, 99%. Now, the test is useless. Everyone's crowded up near the top. The tiny gaps that remain are mostly random noise, and it can no longer tell two genuinely different models apart. The benchmark saturated. But there's a deeper issue underneath, and it has a name. Goodhart's law. When a measure becomes a target, it stops being a good measure. The moment a benchmark becomes the thing everyone optimizes for, models start getting tuned specifically to ace that one test, and a high score quietly stops meaning broad intelligence and starts meaning good at this particular exam. The map gets mistaken for the territory. A number that once faithfully tracked real ability slowly drifts into tracking only itself, and everyone keeps citing it anyway. Then there's a problem that's almost embarrassing, and it's absolutely everywhere. Contamination. Remember how these models are trained on enormous, indiscriminate scrapes of the internet. Now ask an awkward question. Where do benchmark questions tend to live? Very often on the internet. Which means the test questions, and sometimes their worked answers, can end up sitting inside the training data the model already read. So, when you quiz the model later, you are not always measuring whether it can reason its way to a solution. Sometimes you're just measuring whether it memorized the answer key it happened to see during training. The model looks brilliant, and a chunk of that brilliance is plain recall. This is why a single headline score can be so misleading, and why serious evaluation now fights hard to prevent it. Holding tests back from public release, building fresh questions the model cannot possibly have seen, watching carefully for the telltale gap between problems the model was likely exposed to and genuinely novel ones. Trustworthy measurement means testing on things the model couldn't have studied for in advance. So the field is moving past the simple, multiple-choice quiz. If a fixed answer key can be memorized and saturated, you need tests that are much harder to game. One direction is open-ended judgment. Instead of one correct answer, you have the model write a full, free-form response, then compare two models head-to-head and ask which one did better. Sometimes with real humans voting, sometimes with a strong model acting as an impartial judge. Another direction is task-based evaluation. Don't ask the model a question about doing a job. Actually, hand it the job. Give it a real bug in real code and check whether its fix compiles and works. Give it an open research question and see whether its answer holds up under scrutiny. And crucially, safety evaluation. Deliberately probing for the exact failures we've spent this whole series worrying about. Actively trying to make the model misbehave under controlled conditions, so you find the cracks in the lab before your users find them in the wild. The goal running through all of it is the same. Stop measuring the convenient stand-in and start measuring the thing you actually care about. Now pull it all together, because this is where it turns serious. You cannot improve what you cannot measure. Every single advance we've covered in this series, scaling, reasoning, alignment, safety, depends completely on being able to tell whether a given change actually made the model better or worse. If your ruler is broken, you are flying blind, and you might be optimizing incredibly hard in the wrong direction without any idea that you're doing it. That's why, right at the frontier, evaluation has quietly become one of the hardest and most important jobs in the entire field. Building a more capable model is, in a strange way, the part we've gotten genuinely good at. Knowing exactly what we built, what it can really do, where it quietly fails, whether it's actually safe to trust with real responsibility, is the part that's still fundamentally difficult. The systems are racing ahead of us. Our ability to measure them has to somehow keep pace, because measurement is the only thing that keeps us in control of what we are making. That's evaluation, the science of knowing what you actually built and why it's so much harder than it looks from the outside. If this clicked, subscribe. Next, to keep these models climbing, you need more data to train them on. There's just one problem. We're starting to run out.